Okay, welcome at home if you're joining live. Hope that works this time. I was promised the Ethernet is working. We'll get started in a second. All right, good morning, everyone. Welcome back to COMP526. Before we start, let's have a little vote on this one, but probably most people have seen this. If you don't know what Campus Wire is yet, we'll have to talk offline. Let me show briefly what the question on Campus Wire was. That was this one. It's a bit small, maybe. So it basically looks like most people are happy with Ben's plan of not sticking to the letter of the plan in the timetable and instead making use of the slots a bit more dynamically, and in particular using one of the slots for online tutorials only. There's already one person isolating last week, might be back, but there's probably other people who become sick at some point or have to isolate. So I think this is a good idea. If any of you has really serious issues with, for example, being scheduled for the Thursday slot and being totally opposed to having an online only one and cannot make it to one of the Friday slots, then let Ben know as early as possible, as soon as possible, just so that he can start planning these things. If you don't speak up, then we'll assume you're happy with the setup, and so you can go to the online version or you can go to the group versions, as long as the rooms are not too full. I think Ben is happy with you going to whichever group is more convenient for you, and hope we'll try to do it in this not strictly organized way, in the hope that this works out. Okay, so everyone had a chance to vote on this, I hope. I wanted to ask something different before we start. I've been asked this last week. This module is mostly a theoretical module in the sense that we don't build a big project in terms of software or things like this. Most of the ideas are about these eternal truths of algorithmics and algorithms. And so we only use programming on the side and for some of the puzzles. But that said, many of the things are only really sensible to appreciate if you have some idea of how programming works and how some details in some machines are solved. So I like to spice up some of the content this and next week with how things are done in certain libraries. And I know most of you are doing Python, especially if you're on the conversion masters programs. And there's nothing wrong with Python. There's just one detail where Python is not as convenient. Integers in Python have a special representation, which is a little different from what most programming languages do, which are, say, a little closer to the silicon. Python goes quite a bit away from what a CPU natively can compute with. And so if you only know Python and no other language, some of the concepts are a bit less clear because you haven't been forced to think in terms of what the CPU can actually handle. So that's the long pretext for this question. So there's some people who know other things. There's a big blob of Python. Can I get this to show the actual numbers instead of just the, okay, I can see them here. So there's Python with 34, followed by Java with 11 people. Now, what I cannot see from these answers is, are all the people who have other experience in language, are these the same people and they have experience in all those languages? And do we have people who only know Python? I'll try to make some more detailed comments when it's relevant. What's done in Python, what's done in other languages. Just so this is accessible to everyone. If you've learned programming in another language and you haven't looked at what Python does, read about how Python represents numbers. It's quite interesting in its own right for that reason. With that said, I think we can move on. So welcome back to COMP526, and now to Unit 1, the first unit that starts the real journey into our discovery of eternal truths of algorithms. I started last week by saying we want to get to these eternal truths, and they need mathematical statements. If you're only looking at a specific machine, how it's done on a specific hardware, you don't get to this eternal part. And the flip side of that is we need some mathematical models of what's going on. We need a model for the machine, we need a model for programs, and we need a model for data that the algorithms or programs work with. And that's what we'll look at today. Some of the proof techniques from last week will pop up once at some point later in the class. Today we'll mostly talk about definitions, or for this unit. So what's the goal of this unit? First of all, there's an alternative to all of what I'm saying. You could often just take different algorithms, implement them, and see which one works better. If you can do that, if you're actually in the position of doing that in an application, that might be preferable because it's the definitive answer for your specific application. But there's many caveats to this, and often you're not able to do it that way. And definitely on a broader scale, as an academic, as computer science graduates or wannabe computer science graduates, you should have an appreciation for the difference between running time and the analysis of an algorithm, and then these asymptotic complexities. I think this is just the language that computer scientists use, and so you have to be familiar with that. Then in terms of models, we have models for data, the typical ones. You might have seen those before, maybe just not under this term model of data. Look at best, worst, and average case, and sometimes more. In terms of machine models, we'll look at the RAM model, which some of you may have seen, but I'm not sure if any of you has seen the word RAM model in all its details. I like to give this in some detail because I remember when I was taught about algorithms in the simpler model, there was always a gap, and I'll come back to that gap. The word RAM model nicely answers that gap. On the other hand, it looks a little more scary than it needs to be for most of what we're doing, but I want to give this as a background. Then we'll look at asymptotic notation, big O classes. We'll see why we want to use those, and I want you to be able to analyze some simple algorithms, but nothing too crazy. So that's what we'll do in the next hour or so, maybe subject to a little break. And we started late, so let's see how far we get. Before we start talking about the more intricate models, I want to give some intuition, starting from zero in a sense, about what algorithms are themselves. And remember, we need a model for programs, but this is even on a higher level. For me, an algorithm is a sequence of instructions. That's as simple as that. It's like a cooking recipe, hence this picture. Algorithm as a term has attained a different meaning in media, etc., as some combination of a machine learning system plus implications on society, and it's often used in a somewhat negative connotation. But the the meaning of algorithms in computer science is usually restricted to just this. It's some sequence of instructions that solves a problem. So we want to be a little more precise. But what I try to stress here is Facebook, for example, has implemented some system to decide what you see on your feed. And people call this an algorithm. But it's much more than just a simple set of instructions. There's a lot more going in. There's design decisions, and there's lots of machine learning and data bias, etc. So I'll try to be clear that when we talk about an algorithm, it's always this old school algorithm, in a sense, a sequence of instructions with these well-defined properties. So first of all, we want it to be mechanically executable. It should be as precise as needed to be executed on a computer. And that can be painstakingly detailed sometimes. In particular, we can't appeal to common sense of humans. That doesn't work. We have to avoid all fudge. We have to specify everything in detail. A minor thing that you wouldn't normally come across, but in some applications, it's important to make the distinction. An algorithm has to be finite in length. You can't describe how to write an algorithm where you have to write down infinitely many lines of code. It wouldn't really work well with executing that, but yeah. And a last thing is, this is a little more subtle. We want to solve not just a single instance, but we want to solve a generic problem or a generic task. So not just the addition of two concrete numbers, but the addition of two numbers in general, or at least the addition of two numbers from a certain range in general. That distinction is sometimes not so clear, not so formal, but it's usually in the examples we'll look at, it's clear that there's a well-defined algorithmic problem and the algorithm is trying to solve that. A typical example of an algorithm could be bubble sort that probably all of you have seen. The underlying problem is sorting a list of data, say a list of numbers. List usually means it's given in an array, but not necessarily so. And an algorithm for me is again a bit vague. It's the underlying idea how to solve this problem, not necessarily a concrete set of lines of code that does this. So there might be a single algorithm like bubble sort, and you can write different implementations of that same algorithm. For example, in different languages, or even the same language, different implementations that are slightly more tricky and cunning in avoiding certain inefficiencies. So there's the kind of more abstract idea, that's the algorithm for me. I take that this point is a bit vague, but again, in many examples, it's kind of clear. Bubble sort, you could say the idea is that you always compare two adjacent ones, and if they're out of order, you swap them. That's kind of the essence of bubble sort, and you can implement that in many ways in a program. A second term, somewhat related, is a data structure. That's essentially some algorithms plus a specific rule how to store certain data that's associated with this. And again, yeah, this is in examples mostly is more clear what this means. And we'll talk about this at length in Unit 2. So maybe I'll leave it with that. In the main difference between an algorithm and a data structure is that an algorithm runs once. It's, in a sense, a box where you put, maybe that's something to put on this. An algorithm is a box. You feed some input into it, and then it computes, and eventually it spits out some output. That's the traditional model that we'll work with. And a data structure, by contrast, is something that sits there over time, and you can repeatedly query it or change it. You have different operations that you can apply to it. And it has a state that's preserved between those. Most of you will have seen one example, at least, binary search trees. There's many others. We'll come to that in Unit 2 in more detail. Those basic those basic terms clear. As always, I'll try to look at the Slido questions if you want to ask a question, or just scream. Either works. Okay, with these two preparations, let's look at what the analysis of algorithms is like. And what's it for? Why do we want to analyze algorithms? For many algorithmic problems, there are different options how you can solve it. There's different algorithms, and then many different implementations of algorithms, or in other cases, different data structures. And you would like to choose a suitable one for your task, for your application. And for us, suitable or good usually means that it's fast and maybe also uses not excessive amounts of space, but we'll focus mostly on the running time. That's the traditional objective in computer science. And in many cases, this is the core hurdle to overcome. And algorithm analysis is a way to compare different algorithms. So it can tell you, if you have two different algorithms, which one might be more efficient, which one might be faster, or in terms of space, which one is more space efficient. And also a secondary goal is it can make actual predictions, quantitative predictions about how long something will take. And that's important because it means you can then decide if a certain approach that requires you to use a certain algorithm on a certain input of a certain size, whether that's at all feasible. If the prediction is it will take 5 years of computing time, it's probably not the way to go. Whereas if it says it takes 5 seconds and you would rather have it run in 1 second, maybe that's something you can squeeze by working a bit harder on optimizing it. But if the discrepancy is so big, then you know upfront this won't work. So that's the two goals. We want to have a clean way of comparing algorithms, and we want to have a way of predicting how well would things work in a certain scenario. Now you could, as I said before, take the different options you have, implement them, and test it. And there's nothing wrong with that. The only thing to keep in mind is there are some limitations to that approach. You usually test it on some machine, and it's not clear what happens on another machine. Things can sometimes vary a lot. Then you will have to decide on some inputs that you evaluate the methods on. If you're lucky, these are representative for the application you want to use them in. If not, then you will get results that don't really tell you much. And the last point is maybe a little more important in this context. You'll test a specific implementation of the idea, not the idea itself, because you have to implement it in some concrete way to even just run it. And sometimes there's just a little trick needed to make an implementation good, and then you would get vastly different results. And the more abstract analysis can sometimes sidestep this issue. What's definitely clear from an academic perspective, this is not what we want in terms of universal truths. This is the opposite of that. It's very specific to a certain scenario, and it's not clear if it survives a certain generation of computers or a certain scenario of inputs and all these things listed here. So what we would like to focus on instead is have some more abstraction that takes away some of the specifics while keeping those that are relevant, hopefully. And by taking it into the realm of mathematics, we can prove statements. They will be a bit more abstract, but they will be proven and will never be invalidated, unlike the results from experiments. And they will give us concrete hypotheses that we can test. Because every model makes some assumptions, and we can then validate those. But it will be more clear what we have to validate. And as I said many times before, this hinges on having concrete models of machines, programs, and data. So let's start with the easiest one. I think that's the data models. You can take different approaches to this. The most versatile or most widely used ones are these. You can be very pessimistic. You always assume the universe conspires against you and gives you the worst possible input for this algorithm. That may seem a little out of this world. On the other hand, if you can prove a strong worst case guarantee for your algorithm, you're fine because nothing worse can ever happen. So if that's good enough, you're definitely fine. The best case is the opposite. You're very optimistic and assume you always get the easiest input. That's not usually useful for predicting running time, but it's good for looking at the discrepancy between those two. If there's a huge gap between those two, maybe the third one is interesting to look at. And that's if you average over all possible inputs, or some slightly more sophisticated models if you have a good idea for what inputs are more likely to occur in your situation. We'll usually assume, in the context of sorting, for example, we assume that every ordering of the input is equally likely, and we'll work from there. Why do people like these models? They're not necessarily the most realistic for a concrete application. But the big benefit of these models is that they reduce all inputs of a certain size to one number, to one parameter. So we usually we group inputs by size, and sometimes it's not so clear what size means, but in many examples, it's quite clear. If you're sorting, it's the number of elements. If it's a graph, it might be the number of vertices and edges. Some things like this. If it's a matrix, maybe it's the number of entries in the matrix. Sometimes the number of non-zero entries. So this depends on the algorithmic problem, but it's usually relatively intuitive. So you fix the size of the input, and then you stipulate these models. So you take the worst of all inputs for a given size, or the average of all inputs for a given size. And the goal of this is to get the performance of an algorithm as a function of the input size. That's the goal. So we get a single parameter that we assume drives the complexity of an input. Like the underlying assumption behind this is if your input gets bigger, if you have more data, it takes more time to compute whatever function you're computing. And that's usually reasonable because for almost all problems, you have to read at least the data before you can do anything useful with it. And so there's inevitably some dependence on the size of the data. Okay. Now, for the model of the machine, we'll have to spend a little more time on a little detour and look at how we can represent the computers we actually have, but also abstract them to something that is common to all of them. Okay, so this is the delicate part. We want to try to keep a model that's abstract enough so that we can analyze it, but still capture what is the essence of the computers we can build or that you can buy. And the RAM model, the random access machine model, is the consensus model of this to this date. And to motivate this, let's do this little question. So over to Slido. And the question is quite simple, right? It's a computer, so it should be able to add numbers. But how long does it actually take to add two numbers? I'll give you one more moment. Always the question that sparks discussions. Now I should have paid attention where we had before. We had 57 votes on the last question, 47 on the first. Maybe we can get a few more people.
Are we assuming constant point on word size?
That's the trick, yeah. So you're quite right. In a sense, the question is ill-posed, but that's only for those who thought about the right model. Let me lock it now. And I would say there's different answers that all make sense. Okay, no idea what you're talking about is correct too, but that's basically correct because I know you're coming from very different backgrounds. There's definitely two things that you can say that both make sense, and they seem to completely contradict each other. You can say constant time, which is true if you have integers that fit into one word. As one of you said, today's computers usually have 64-bit words. Most of them have. And so if you have an integer that fits into 64 bits, then you can add those two in, well, roughly one clock cycle. It's probably not quite true, but there's pipelining going on, and there's in a constant number of clock cycles for sure. And maybe the definition of what exactly is a clock cycle is a little less clear with the complicated architectures. But that is correct if it fits into one word. If the number is vastly bigger, as for example in the case of some cryptography, some crypto applications like RSA, where you need really, really big integers, then it's rather proportional to the number of digits. In a sense, it could be even worse. If you, for some stupid reason, decided you want to represent your numbers as unary, so the number of, you represent them just with a sequence of ones, and the number of ones is as long as the number you want to represent, then the answer would be exponential in D. No one does that, so it doesn't really make sense to put it up. But yeah, there's different answers to this. And they all kind of make sense. So how can we possibly have two answers when they contradict each other? So the reason is that we need to somehow let our model know how big the integers are, right? Let's go back one step. The machine model itself, what does it do? It not only tells you how things are computed, but in a sense, it also dictates what our algorithms or what programs for this machine look like. And so that's essentially defining what are algorithms for this model. It can usually describe how these are written down. And then you can allow something like pseudocode to abstract from that, but you could, in a sense, work directly on the language of the machine. So the machine model also describes the programming language in a way, the lowest level at least. And it usually defines a cost model. This is a little more subtle, but if you think about it, it's quite clear. The machine has some way of executing code, and that implies there's some time it takes to execute code, and that depends on how the machine operates. So the machine model also defines what is running time. I've talked about this trade-off before. We want it to be detailed so that it captures what's going on in certain machines that we want to use in applications at the end of the day. But we want it to unify what we have, where these machines differ. And ideally, it should also be simple enough so that we can mathematically analyze it. The real answer is there's more than one model that try to strike a different balance between these. And we'll try to stick to one that's closer on the simplicity side. That makes it easier to analyze it, but sometimes misses out some things. I'll point out some of these when we get there. And so without further ado, here is the model that's the random access machine. And I want to briefly go through what it looks like. Again, we won't really build on this at this level of detail, but I want to make sure you know about it, because this question about how long does it take to add two integers, it is very cleanly answered in the word RAM model, and in any other model I've seen before, it was still kind of fudgy and not quite well defined. So we assume we have an unlimited memory, which is essentially one big array. So you can say there's a first cell, 0th cell, first, second, and so on. And you can use as much memory as you want. You will have in a way to pay for it, but there's no fixed limit. Now this seems a weird model, right? We can't really build an infinite machine. What we do have in machines is the option to extend them as you go. So you can think of whenever you run out of memory, you order more memory and attach it to the machine. That's still not really infinite, but this is also not what it says. It says it's unlimited, which means there's no fixed limit. That's not the same as infinite right from the start. We'll have registers. These are just variables that can store an integer, and we'll have a fixed number of those. I don't want to put a specific limit on those, because it's often convenient in a program to assume you have a few more if you need a few more. You can think of it as around 100 or so in current CPUs. It will be convenient to say we can borrow a few more if we want, but it should not depend on the input size. That's the important part. It's fixed. Now, what can these registers and the cells in the memory store? They each store a W-bit integer. So that's the important part. It's not just any integer, it's an integer of a certain size with a certain number of bits. And the W itself is a parameter of the model that you have to kind of specify for the machine to make sense. We'll assume that these are just positive integers, but you can redefine things in your program to pretend they're also negative. So this is the basic model, and then you can make your program work with it in any way you want. What can you do on this machine? Basically 3 types of operations. You can load or store a single cell from or to a register. And it's important to say here that the location in memory from which you load or to which you store a value is also taken from a registry. So you can do something like indirect addressing. The address where you go to is taken from another register. So your program can compute the address. Then on the registers, we can compute. That's the actual computation going on. We can add numbers and all the other arithmetic operations. It's all integers, so keep that in mind, that something like division only makes sense in the integer sense. So you round down or you take the remainder. And all arithmetic by default is modulo 2 to the w. So this is what actual machines do. It's exactly taken from how CPUs work. And it's not usually a problem. On top of these arithmetic operations, we also allow bitwise operations. I don't think we ever use this in this module, but this is part of the word RAM. So you can do bitwise and or XOR negations, which allows some extra tricks sometimes. And the third type of operations is control instructions in your program. You can jump to a different location in the program, and you can make that jump conditional on some register. So you can ask, if that register is 0, jump here, otherwise don't. That's all you can do. The cost measure is quite natural, I guess. It's just the number of executed instructions from these 3 classes. And that's all you can do. So that's quite close to what current CPUs are like, except for one little weirdness that I skipped over. And that's this statement. So remember, n is the size of the input, size of the data you want to work with. And now this statement says, so this symbol is taken to be proportional to. So this says the number of bits in a single word grows with the input size. That's probably a weird concept, so let me write this down. You would think this is not really what computers do. They don't somehow just double. However, if you look historically on different computers, how the word size has increased, it's not so far from this. It's actually quite well described by this relation. Word size is roughly the logarithm of the input sizes. It just happens to be maybe the other way around. If you have a certain word size, you can work with a certain size of data, but this is not, it's not automatic. It's quite striking that this matches the historical development. So the machine grows with the input only means as a model. You can make the input bigger and bigger, and then if you need to work with inputs of a certain size, you would have to build a machine with the appropriate word length to do an algorithm properly. And there's another more intuitive reason, maybe, if you want. Think of n as the number. You're given your input is one big list, an array. Then that would take up n input cells. So what that condition then means is you can describe one position in this input in a single word. That's the condition we want. Maybe that's some somewhat intuitive condition. Okay, for now, take it as the definition, and in case of doubt, this is what you should look at for asking the questions. What is the actual running time? And so again, our question about how much time does it take to add two integers, it is proportional to d if you have d digits divided by w, because you can work on w digits in one time step. So if originally your numbers were small enough so that a constant number of words can hold them, addition takes constant time. If they're bigger, if they take a linear number of words, it takes linear time, and so on. So this model clearly answers that question without any resort to, if this is the case, then this, and if that's the case, then that, and in between, I don't really know. You can imagine how if you program a RAM with these three types of instructions, this is very, very low level. It almost is like an assembly code for some actual processors. So this is quite inconvenient. What we usually do is instead write pseudocode. So that's code that's supposed to be clear enough for an average programmer to turn it into the description that the machine can understand. Now, average programmer, who knows what that is? But I'll just make some assumptions about our average programmer, and we'll have to live with that. The second simplification we'll make is, instead of counting the exact number of instructions on the RAM, we'll count dominant operations. And that's a bit problem specific what that means. But for example, it could mean the number of array accesses. The idea is that the overall running time will be proportional to the number of these dominating operations. And you will have to find what operation that is. And again, in many applications, it's quite clear what is a suitable choice. The important thing here, I want to stress this again, if you have this abstract model, in both cases, you can go into more detail if you ever wanted. That's the idea. You should always be able to. If you have pseudocode, you could translate it to actual instructions on the word RAM. And you could, instead of doing the dominant operations, count the exact number of instructions on the word RAM. It's inconvenient, it's tedious, it's often not needed for getting the statement you want, compare algorithms and predict how long they'll take roughly, but you could. That's the beauty of the detailed models. Before we continue with asymptotics, questions about word RAM, and is everybody clear about the D-digit addition now? So this might be something I want to put on the slides. I said this before, but didn't write it down. How much time does it take to add 2 D-digit numbers on a W-bit word RAM? Does anyone remember and wants to tell me? D over W, because I can work with W digits at a time. And remember, W is not a constant. W depends on the input size. So W can be log n. If D is well, it depends what n is. But this can be anything between constant and linear in D. Okay? So just to finish that off. Were there any other questions? Check Slido. Nothing on CoMP526. I think we're good to go then. Except that it's roughly, maybe it's time for a little break now. So let's continue 11:49.
Hey, I got a stupid question that why the global variance is not in real time for many progressions, and I just met this problem for many times.
So you mean
previous tutors told me.
say again, the global what?
The global variable is
Okay.
is the formula is not very common to many.
So you mean it's not with style?
Yeah, it is not a strategy.
Okay. I mean, I think there's global variables are not bad, right? They're not evil. It's just so if you build a big project, you want to keep things isolated, so that if you change something here, it doesn't affect the component over there. And global variables, if used in a nasty way, could mean that if you change something here, that affects the global variable. And this one also reads that. So you get this coupling between different components. I think that's why people don't like it. But it's not an evil concept, but sometimes it's a convenient and efficient way.
So it means it is just just separate the project by layers.
Right. That's what I would say.
And that is to line this rival being just being disturbed by the other
Say it has the danger to be like that. It could mean that things influence each other and people don't like that. There sometimes is a second concern. It could mean that parallel code is slower if you use global variables. That's I don't know. know where this question popped up, but
So
there's a cost to synchronizing the caches of different cores. So that's another reason why people don't like global variables in this context. I don't know if that's...
yeah, I was just afraid that if I will use that handle statements or exam,
I see. No, global variables are not evil.
okay. So
Just in big projects, it might be smart to avoid them. Yeah.
okay, thank you.
Sure. Yeah.
So, while I was going to the model, so can you just please explain me the that you have shown that W is proportional to the law or something? Yep. Can you just explain
What part? I mean, the proportional part, or well, suppose you're sorting a list of numbers, okay? And suppose the numbers are all small, they fit in one word. Then maybe the input size is just the number of numbers. And then you would say W is log n bits. Okay, maybe the proportional means it's also fine if it's 10 times log n.
and that's the only thing. And you're talking about the pseudo. So are we having like in exam like we have to write both algorithm or do we have pseudo algorithm and pseudo?
I think you will only work with pseudocode in the exams.
So just we have to describe how it works and we don't have to go that deep.
Not normally, yeah. I think if then on the level of explanations, say if I was to ask you how long does it take to add two d-digit integers or similar things, then I'd like you to be able to reflect what this means on the word wrap. Right? But we won't write code on the word wrap for this.
We are guaranteeing the time actually, but I mean, we're gonna go average case on. We're gonna calculate average case, worst case, or
We'll see examples, yeah.
because for example, according to worst case, much better than.
Sure. Yep.
But to be honest, a lot of people prefer quick sort to first sort.
Yeah, I mean the reason is you don't ever see this worst case, so why would you bother?
Why? Because
Yeah.
it's so.
Yeah, that's exactly the thing, right?
We're gonna.
We'll talk about exactly that part in Unit 3 in detail. It will come up in some cases. We'll talk about it in the context of randomization again. This is not just average case. You can actually force the average case, right? Yeah. Okay. We'll come back to that. All right, everyone. Looks like 11:49 has passed on my clock. So time to continue. After we've defined our models, we noticed that for a clean model of machines and algorithms and data, we always need this dependency on n, or something that grows beyond bound. And we'll see that this is really baked into algorithmics. You always want to look at growing inputs, and that's why this last section is important. So in this last section, we'll look at asymptotics, big O classes, and also motivate a bit why we want to have this tendency to make things grow to infinity. So let me start with why do we look at asymptotics? As a fact, algorithm analysis usually focuses on large inputs. And by large, I mean sufficiently large for certain statements, and that can be really large. And the reason for that is threefold. First of all, it abstracts from some unnecessary detail. Many algorithms need to treat very small cases slightly differently from the general case. Again, something that might make more sense on examples. And how you exactly deal with these little base cases is not usually that interesting or important. And a formal way to say that we want to ignore those is to look only at large inputs. It happens to simplify the mathematical analysis of algorithms, something we'll come to, and the reason you can already look at below. And the third one is for the other task of algorithm analysis and all these modeling efforts was to compare algorithms. When we have several algorithms for the same algorithmic problem, we might want to know which one is better. And as just was also the topic of some questions, sometimes these measures contradict. And so you have to decide which way to go. And one way they can often contradict is algorithm A is fast on inputs up to 100, but then for bigger inputs, algorithm B is better. Now, it depends on your application. If you actually have many, many calls to tiny inputs, then maybe algorithm A is interesting. But most of the time, this is not the dominant cost in an application. So instead, you want algorithm B, which is good on big inputs. So for making a proper comparison between different algorithms and make that comparison conclusive, we often need that assumption that we look at large inputs. Asymptotics is all about an approximation when something gets large, when a parameter gets large. In our context, we will always think of the input size n going to infinity. So it's always an approximation for n around infinity. You might have dealt with approximations for functions in some other contexts. I don't know, engineers often use Taylor series approximations to functions around a certain point. This is what your calculator does if you call the sine function or the logarithm function. They all use some Taylor series expansion, which is an approximation of a function, which is complicated, by some simple function around a certain point. And computer science does the same. It's just that we use this around infinity. So the techniques are sometimes a little different. And to motivate this more concretely, let me look at this function. So let me read this out to make it sufficiently scary. Suppose there was some algorithm that has the exact running time f of n, where f of n is given by 2n squared minus 3n, and then the log to the base 2 of n plus 1 rounded down, plus 7n minus 3 times log of n plus 2 rounded down, plus 120. I mean, for whatever reason. But stuff like this is sometimes the output of a precise analysis. If you go count the exact number of instructions on the word RAM, some people have done this, like like one standing in front of you. But I made this example up. But we can maybe agree that this function, there's a plot, is kind of ugly and nasty to work with, whereas a nicer function is just 2n squared. And here's another plot. So the red plot, hope you can see the difference. The red plot is for the red function, a very simple function, but it well approximates the black one. And you see in this case, I just had to take this first summand, and it happens to be a good asymptotic approximation for that function. That's the kind of simplifications we're after. We try to make the function that's otherwise complicated. It has these jumps at powers of 2 or powers of 2 minus 1. And so all of these weird things that happen in the original function. And we replace this by a much simpler function. So let me formally define what asymptotics for us is. We'll not always need to work with this definition, but I think it's very important to have one concrete formal definition of this on the slides. So bear with me for a second. We'll do an example after. I'll start with this simplest version of asymptotic notation, which is the tilde notation. So f and g are asymptotically equivalent, written like this. If when I take f divided by g and compute the limit as n goes to infinity, the limit is 1. That's the first thing. And then I would like to treat these two functions as asymptotically equivalent. because they give the same value for large n. And you might notice I use this tilde symbol here, and this is not by a coincidence. Those two functions are asymptotically equivalent. A more widespread use of asymptotics is the big O notation. I'm sure you will have seen this. So we define a class of function. O of g of n is really a set of functions. And so the proper way to say f is O of g of n would be to write element, because f is an element of this set of functions. But pretty much all around the world, people write equals. I think this has historic reasons. People started typing algorithms papers on typewriters, and it was just absurdly inconvenient to write so many element symbols. It's mathematically bogus, and it confuses first-year undergrads all the time. But I mean, you're an MSc student, so you can probably deal with it. I put an element sign on this slide, but probably for the rest of the module, I'll go to the convention that the rest of the world follows. You'll have to live with it. So we say f is in O of g if, again, I take the same quotient as before, but this time I don't require that it converges to 1. I require something weaker. I take the absolute value and then say that this remains bounded. Another way of saying this quotient doesn't go to infinity. Okay? And you can also write this using lim superior. I don't know if this helps you at all. If it does, great. If not, you can ignore it. The important part here is we allow up to a certain value n0 that this is not even properly defined. It could be that g is 0 for a while or something like this. We want to ignore that. But starting from a certain value n0, this quotient has to stay bounded, has to stay below a certain value in absolute terms. All right, I guess you've seen this, but maybe not exactly this definition. And I think this is a good definition. I'll show you why. There's two variants of big O. Big omega is the other way around. F is omega of g if g is O of f. And big theta is the combination. F is in g, in theta of g if it's in O of g and omega of g. So then they're, in a different sense, equivalent asymptotically, but not as strictly. There's, we'll come to that. There's a third version of asymptotic notation that I think you will sometimes encounter. That's the little o and little omega. And that's a stricter version. So here we say that this quotient has to go to 0, as opposed to just stay bounded, not go to infinity. Now it has to go to 0 exactly. Okay? For most intents and purposes, you can replace this formal definition with this intuition. But again, in case of doubt, go back to the formal definition. F is O of g means something like f is at most g, but with a caveat or 2. So let me write this just in quotation marks. So f is O of g means f is at most g, but up to constant factors. So I might have to scale up g by a certain constant, but fixed, not depending on n. And only for sufficiently large n. It might be that they do whatever up to a certain point, but after that, f stays below c, some constant times g. Okay? That is big O. And of course, you can derive this from the definitions, but because we'll use those two mostly, here's the picture for big theta. That means f is roughly equal to g of n. But again, same two caveats, up to constant factors only. So I can bound f by g from below and from above if I multiply with a certain constant. And I mean, obviously, c1 will be a smaller constant, c2 will be a bigger constant. And again, this only has to be true up from a certain point on, for sufficiently large n. Okay? So that's the intuition. You can often just look at pictures like this and guess what the asymptotics will be. But I want to point you to a really nasty example that maybe shows why these things are not always quite so clean. You don't have to read the text. What I want you to look at is this plot of two functions, the green and the red one. And this goes up to 2000 and up to 2000. And it looks like, okay, initially green is bigger, right? But red has a higher growth, so a higher slope, so it picks up. And it seems like from this point on, red will be bigger, and it looks like it will be substantially bigger from then on. If you zoom a little further out, up to 10,000, this indeed seems to be confirmed, okay? So here we have the point where they turn over, and this seems to suggest, yeah, red just grows much faster than green. But if you zoom out further to 200,000, look how they flipped again. So there's another turning point at around 50,000 where the two cross. And now it suddenly looks like the green is growing much faster than the red one, right? And these are two concrete functions. Here they are. They're nasty. They're made up. It's an example that's contrived. If you look at a doubly logarithmic plot, you see what's going on. The two are oscillating around each other, and they're actually asymptotically equivalent. Their limit goes to 1. But from just looking at these plots, it doesn't look like it. So be wary. Don't trust the plots. Only trust mathematics, or limits, rather. But still, in most cases, you can write down conditions on the functions. If they don't do this weird oscillation, you will not see this kind of behavior. So there are many special cases where looking at the plot like this is sufficient. Just in general, be careful. All right? Good. If you have questions, you give me a shout. Let's do a quick test if you're paying attention and or know this already. Okay, numbers are shooting up. Give you one more second. This is not supposed to be a mean question. It's one of these, are you guys awake? I also notice here, I used the element symbol here and then the equality down here. This is not where I'm getting at. I should have been consistent on this question. Just shows how deep this is contained in me as well, that these two things are the same. So let's say we lock it here. And this is the intended answer, but I also give you a go for the last one for a reason I'll come to in a second. If f is in, so let's just go back to the picture briefly. The way to think about it, this question just tests your understanding on this intuition. If f is O of g, that means f is essentially smaller than g with the two caveats, right? Up to constant factors, sufficiently large n. So if you flip this around, if you ask what is g in terms of f, then g is bigger than f, and the symbol for that is omega. So this is essentially what I wanted you to answer, but if f is identically 0, for example, then you might say 0 is in O of g for some functions. That still kind of makes sense. But nothing can really be in omega of 0 in a proper way because you divide by 0. This is okay, it's a bit of a corner case. If this is what you had in mind by ticking the last one, well done. Pat yourself on the shoulder for catching this little corner case. If not, you can basically ignore this unless there's something broken with the definition division by 0. The intended answer is the second, and it's just this. If one is smaller than the other, then the other is bigger than the former. Okay? Let's do a quick example just to see why I like these definitions that I gave you over some others. So the alternative that people often give for f of n is in O of g of n is there is some n 0, and then for all n greater than 0, this function is less than c times that function, stuff like this. I think this is fine, but there's nerdy nitpick reasons why I don't like that, and there is the practicality issue. If you want to test something like this, is this nice function 20n cubed plus 10n log n plus 5, is that in theta of n cubed, or is that tilde n 20n cubed? What you really do is compute a limit, and that's it. You don't mess around with finding n zeros. So let's see. We take the long function, and you have to check if I'm computing correctly this time. Unlike that little thing on last week. So I'm taking this function. That's my f. And that function, that's my g. And I'm testing now whether f is tilde of g. Okay, that's the first thing we want to prove. So I'll take these two, and I compute the limit as n goes to infinity. Now, the easiest way, this is a fraction where we have a summation in the numerator, so we split this. So we have 20n cubed divided 20n cubed, that's just 1. And we're left with another limit with the remainder. And you can show that this is 0 in various ways, but this is basic real analysis now. I don't want to go into that. There is a tool, Wolfram Alpha, just in case you're not sure. Now that brings me to the question on this sign. We will eventually have an exam. I have yet to learn whether that will be an online exam or an exam on campus. The only thing I know is that it hasn't been definitively decided yet. If it's online, there's no way I can stop you from using Wolfram Alpha, so I would allow it, or I allowed it in the past years. If it was on campus, there's no proper way to allow it without allowing you other things, so I would not allow it, but then make the tasks easier. Either way, if you want to be sure for the exercise problems, you can use Wolfram Alpha to compute limits, because, again, we're not a real analysis class. This is about practicing the asymptotic notation, so I'm fine with you using this. And limits like this, either you know it by heart anyways, that n cubed dominates n log n, or you compute the limits. And, well, here you want to use L'Hopital's rule, and it's not complicated, but not what I want to spend time on. Okay, so we proved this part, the tilde part. I can take the same proof basically works if I do away with the 20. Let me just make that gray. And then this would turn into a 20, but the rest would be the same. So now I have divided this f by a different g. And the outcome is 20. The limit of this quotient is 20. So if you go back to the formal definition, for big O first, we divided f by g, and we got 20. 20, even take an absolute value, remains 20, and it's definitely bounded. It's, for example, below 21. And so we've shown that f is in O of g. So this part also proves okay. Now we would also have to do the omega part. For that, we have to take the quotient in the opposite direction. We divide g by f. So if you do that with this limit, everything flips over, and the result is 1 over 20, but that's still bounded. And so we also get the omega result. If you've done asymptotics before, bear with me. I know this is like a baby speed in a way, but I want to give everyone a fair chance to learn this before we use it all the time. So that proves O of f is O of g, f is omega of g, together big theta of g. So that proves this part as well. Okay. Let me briefly do this second example. So we take again the first function divided by the second. Now you may remember if you have an exponentiation inside the log, you can pull it out as a factor. So that's the same as 3 times 2 log n plus the log n. And then we divide by log. And here you may note that I didn't put the base of the log here. So if I write log, that's something to point out maybe. LG always stands for log base 2. We have a special symbol in computer science because we use it all the time. Guess why? Ln is the natural log base e. We don't ever use log base 10, so I don't have a symbol for that. I do use log without anything only inside big O classes, because as we'll see, it doesn't matter which base you take as long as it's constant. So it's that's my notation. It's not completely universally agreed upon. But if we divide by log here, we might as well take any base as long as it's constant. So we can convert it to base 2. And so again, if we take the limit of that, you notice you can write this as 6 plus log n divided n. If I take the limit, that's 0. So let me cut this short here. Again, something you can check with Wolfram Alpha, or you take L'Hopital's rule twice, and then you're there. And so the quotient remains bounded because it's 6. So that proves big O. If I take the reciprocal, the quotient, the limit is 1 over 6, which is also bounded. So I also get the big omega, and together that's the big theta, same as before. And the last one doesn't even need a proof. It's just there to point you to something that's somehow a little absurd. I think that number is called 1 Google, where Google got its name from. Legend has it did. But it's just some number. It's an absurdly huge number. But of course, if I divide it by 1, it's still an absurdly huge number that doesn't change, doesn't grow with n. So it remains bounded. The quotient remains bounded. So this statement is correct. It also means if we're using asymptotic notation, in particular the theta classes, big O classes, we're ignoring constant factors, which could be 1 Google, which might mean that the statement is very, very crude. Luckily, in most cases, most algorithms, these constants are not that bad, and so they make proper statements. But there's examples known in rare exceptions where indeed the constants you're ignoring are so big that you shouldn't ignore them. Most of the time, we're lucky. And if you're in one of the unlucky cases, you should try to prove a tilde result instead, where the constants are not ignored. Okay, let's try another one, just real quick. And then we'll move on. So it's sine n plus 2 times n squared and theta of n squared. Anyone still busy? I think there's a few people left. Aha, votes are trickling in. Okay. So most of you got this right. The thing is, you divide, switch back. It's true. And the reason is you divide the sine n plus 2 n squared divided n squared. Take the limit of that. That just cancels. Now, you can't really compute that limit, right? It doesn't converge. So this is one of the cases where you work with the actual definition. And you can still say sine is never bigger than 1, even in absolute value terms, and it's a plus 2. So this is never bigger than 3. And also, it's never less than minus 1, so plus 2 still makes it 1. So this quotient for any n is between 1 and 3. And that's enough to show that the quotient is bounded and the reciprocal is bounded. So that gives you the theta statement. Okay? So that's one example where taking limits doesn't work directly. However, if you type this into Wolfram Alpha, it wouldn't just say, I'm broken, I can't deal with it, this doesn't converge. You would actually say the limit is the range from 1 to 3. It's pretty smart in this sense that it still gives you a reasonable answer, which is good enough for answering this question. This is a quick cheat sheet of useful rules how to work with these asymptotic notations. Just very briefly, if you have a constant factor, you can ignore that in theta classes. If you sum up two functions in theta, that means the same as taking the bigger of the two. And here are a few often occurring orders of magnitudes or theta classes. You can have logarithmic, as I said before. Any constant base of the logarithm doesn't change the theta class because you can just pull it out as a constant factor. Linear is something that often occurs, and again, constant in front of it is ignored. Linear arithmetic is a bit of a portmanteau of linear and logarithmic. It's just n log n, right? Quadratic sometimes, yeah, and you will often hear in other contexts, in complexity theory, people talk about polynomial time and exponential time as the big things to contrast. And here's the formal definition for those two, but we won't really need this much because we're focusing more on the efficient algorithms. That's mostly a cheat sheet for you to come back to. I want to finish with a last little example. And then we should have a few minutes left to briefly look at the prior knowledge survey. So last little example on asymptotics. that combines two things. It shows an actual algorithm, and it gives another little corner case caveat. So this is an algorithm for computing x to some integer power. So it's computing a power. Now you could, of course, take x and just multiply with itself m times. Now, it'll depend on the word RAM how big the numbers are, how long this takes. But I want here to say, let's keep things simple. We only look at the number of multiplications. Okay, so our cost model here is a bit more abstract. We don't care how big numbers get. And of course, if you just multiplied the number m times with itself, then that would be cost m, or m minus 1. And this algorithm can do it a little smarter. So this is written in Java code, but I hope this is understandable, even if you're not very familiar with Java. So this is x. We pass in x, and we pass in m in binary. We already split off the binary representation. And so what this algorithm does, it starts with 1, and for every bit, it always it iterates through the bits of m. It always multiplies the result with itself, which means it squares it. If the bit is 1, you also multiply with x. Okay? And you can think about that this always works and computes x to the m correctly. And how long does it take? Well, roughly, we'll see in a second. So first of all, let's give some names to the input parameters. Let's say m is the number of digits. Sorry, m is the binary number, this number, and n is the number of bits in m. And x is given as some floating point number, so we assume that this fits in one word. And so then we only have to compute the number of multiplications. So how many multiplications do we do in total? We'll run through this loop n times. So that gives us n multiplications from here. And the second time we do multiplications is in this if case. So, well, that depends. It's the number of 1 bits in the binary representation of m. That's the second summand. That's the additional number of multiplications from here. Well, okay, there's line 5 already written. Maybe that's enough. So what we can easily see is that the number of multiplications is between n and 2n. Okay? Because the number of 1 bits, it could be 0 or maybe 1. But let's be generous. It's at least 0. And at most n, because n is the number of bits in m overall. And if they all 1, then this is the maximal value. So now I would like to ask you, what can we deduce from this knowledge and this knowledge alone? Let's see where that question is. Sorry, Slido is stuck. There we go. I think it's insightful to post this question, so let me give you a minute. It's the last slide anyways. So worst thing is that we don't have as much time to discuss the prior knowledge survey. I think that's okay. So what I mean by most precise asymptotic statement is one of the things So C of n equals and then something or tilde or something. And you should give me the most precise you can think we can make. It's a little tricky. It's a bit more than what we've done before. Okay. Many of you voted for theta n, and that's the answer I was after. Just give me 1 minute to make that last point. So this is the correct answer, theta of m. Sorry, theta of n, which is theta of log m. Here's a plot of this function, the blue one. So please, this last point down here is important. We can usually think of theta meaning that one function is asymptotically equivalent to another function times some unknown constant, and we don't care about the constant. Except in some cases, there is no such constant, like in this case. You see this blue function definitely is not a constant times the red or green. It oscillates between the two. And this is allowed for theta. So theta is sometimes more convenient, not just because we ignore the constant, but we can't actually nail down any constant. OK, that's the end of that part. What I want to do is show a little bit of the prior knowledge survey, but this is just for your interest if you're curious. If you have to be somewhere else, that's up to you. So we overall had 66 people answering. It was set up as a quiz, so you got some number of points, I guess. And it was up to 13. Why does it show 14? And you see some people did this well, and the bulk is much lower, and this is fine. You know, remember, I asked lots of questions where I didn't really expect the majority to know this. But I think this also shows you how diverse you as a lot are. And so I'm constantly trying to strike a balance between not boring those who've seen it before and not completely losing those who haven't seen it. And we have both. The statistics of the different courses are we have more big data high performance computing than the past. Other than that, it's similar. Many of you seem to at least consider doing a PhD. So then for you, the theoretical part of this module might be useful as a preparation for that. So computing with fractions and these things worked fine. And many people figured out what an integer can be in Java. More interesting was the second limit, this one. Only very few got this one. If you remember, this is E. It's one of the definitions of E. Either you know this or you don't. There's not much. There's not much to do. This one was better. The abstract data types, quite a few people got this fine. We'll discuss this next time. Binary search trees we'll discuss next time. The most fun one was this one, which nobody got the right answer to. It was also the one where the number of options is the entire alphabet, so maybe there's a correlation. In principle, this task is quite... Guys, you gotta go? Okay, then see you next time. If someone wants to stay and discuss this further, I'm happy to stay, but I don't want to hold you back from your next appointments. See you on Thursday. So I'm still on the live stream. Not sure if I keep that running for more of this. Give me 1 second. Let's see how many people want to stay and discuss the rest, or if you leave it with that. Just give me a second. Let's see how many people want to see the rest of this, and then we can cover the questions. Sorry for that. Can I ask, is someone staying for seeing the rest of the questions, or do you have different questions? Anyone staying? I'm asking whether I close the live stream. You know, this is how it is with professors. They keep talking if you don't stop them, right? We can discuss the last question about Java semantics. This is again something not so vital for this module, but if you want, I can explain why D is the right answer. That has to do with the definition of dynamic binding. Any questions on the prior knowledge survey? Should I go back to some specific point? There's no other overall statement. My main point is you're very diverse. There's people who are definitely bored from anything we've done up to now, I think. And there's people for which everything I said was basically new, I think. And so this is, yeah, my point to make is to show you this, also show you where you are in how much you already know. There will be definitely points that are not boring for any of you. I'm just trying to bring everyone on the same page before we go there. That's all in the prior knowledge survey, unless you have questions.
So we'll be mostly using Java for all the explanations and everything?
Not much. Python has the problem that if I ask a Python programmer how much time does it take to add two integers, he will say, I can't know, because Python, if he knows his Python, Python integers are actually unbounded size. So they grow as much, they use as much bits as they need, because they're essentially a string of digits. Now, if they're small enough, they would probably fit in a word, and they would probably be dealt with in one word operation. But I'm not even sure if that's true. And you wouldn't see the difference. In Java, you're forced to think about, is it an int that fits in one word? Then you use the type int. Otherwise, you use big integer, which is an unbounded type. But you have to consciously make that decision. And that's why I'm unwilling to convert this unit to Python, because it completely blurs that distinction. The assignments are already ported to Python because it didn't make much of a difference. This one code, the exponentiation, I might as well do this in Python. There's no great reason to use Java, except that maybe you want to stress the floats. But I might as well just say it like I did. I don't think we use Java much. I put this there just to see how deep into programming people are. But if you're not ever doing Java, then It's clear that you can't really know this answer. Was that what you wanted to ask?
No, I mean, in gen, I've done a bit of Java, but
Yep.
I'm not really very much. I don't want to do Java again.
Well,
I see.
Python
Yeah.
first.
Well, yeah, I mean, this is a controversial topic. Whatever language you pick, some people will like it and others not so much.
I just want something with types, explicit types.
Yeah, explicit types. I like explicit types too. That's a different issue though, right? Yeah, this is more about software engineering and
I think
being clear
that's
about
why we
code.
can multiply int and string in Python, but actually quite freedom.
Yeah, well, Python frees you from many things that is convenient. Okay, let's close this with a discussion. There's many languages we like. We will mostly work with Python for whenever you have to write code. I'll watch out what else I have in terms of references to Java. I think the other things are mostly, if we're doing a certain data structure, there is an implementation of this data structure in Java, and it's called like this, which might not help you very much. And some of these don't exist in Python. Python might be the only language I know that doesn't have an implementation of binary search trees in the standard library. It's another good reason to hate Python. No, I don't hate Python. All right, I'll close the live stream now before I talk myself into trouble. Bye guys, see you on Thursday.